Traits. Defining shared behavior. A trait tells the Rust compiler about functionality a particular type has and can share with other types. We can use traits to define shared behavior in an abstract way. We can use trait bounds to specify that a generic type can be any type that has certain behavior. Note: traits are similar to a feature often called interfaces in other languages, although with some differences. Defining a trait. A type's behavior consists of the methods we can call on that type. Different types share the same behavior if we can call the same methods on all of those types. Trait definitions are a way to group method signatures together to define a set of behaviors necessary to accomplish some purpose. For example, let's say we have multiple structs that hold various kinds and amounts of text. A news article struct that holds a news story filed in a particular location, and a tweet that can have at most 280 characters, along with metadata that indicates whether it was a new tweet, a retweet, or a reply to another tweet. We want to make a media aggregator library that can display summaries of data that might be stored in a news article or tweet instance. To do this, we need a summary from each type, and we need to request that summary by calling a summarize method on an instance. Listing 10.2 shows the definition of a summary trait that expresses this behavior. Pub trait summary, function, summarize, reference to self, return a string. Here, we declare a trait using the trait keyword and then the trait's name, which is summary in this case. Inside the curly brackets, we declare the method signatures that describe the behaviors of the types that implement this trait, which in this case is function, summarize, reference to self, return string. After the method signature, instead of providing an implementation with curly brackets, we use a semicolon. Each type implementing this trait must provide its own custom behavior for the body of the method. The compiler will enforce that any type that has the summary trait will have the method summarize defined within this signature exactly. A trait can have multiple methods in its body. The method... Well, that's not what I was trying to do. Okay, a trait can have multiple methods in its body. The method signatures are listed one per line, and each line ends in a semicolon. That's what I was trying to do. Implementing a trait on a type. Now that we've defined the desired behavior using the summary trait, we can implement it on the types in our media aggregator. Listing 10.3 shows an implementation of the summary trait on the news article struct that uses the headline, the author, and the location to create the return value of summarize. For the tweet struct, we define summarize as the username followed by the entire text of the tweet, assuming that the tweet content is already limited to 280 characters. Pub struct news article, fields pub headline string, pub location string, pub author string, pub content string. Implement summary for news article. Function summarize a reference to self, return a string. The body. Format. Something by something something. Self.headline, self.author, self.location. Pub struct tweet. Fields pub username string, pub content string, pub reply bool, pub retweet bool. Implement summary for tweet. The same signature. So function summarize reference to self return a string. The body is format. Only two things. Self.username and self.content. Implementing a trait on a type is similar to implementing regular methods. The difference is that after impl, we put the trait name that we want to implement, then use the for keyword, and then specify the name of the type we want to implement the trait for. Within the impl block, we put the method signatures that the trait definition has defined. Instead of adding a semicolon after each signature, we use curly brackets and fill in the method body with the specific behavior that we want the methods of the trait to have for that particular type. After implementing the trait, we can call the methods on instances of news article and a tweet in the same way we call regular methods, like this. Let tweet equal an instance of the struct tweet with fields username, string from horse ebooks, content, string from, of course, as you probably already know, people, reply, false, retweet, false. Print line, one new tweet, and then tweet.summarize. This code prints one new tweet, horse ebooks, of course, as you probably already know, people. Note that because we defined the summary trait and the news article and tweet types in the same libers in listing 1013, they are all in the same scope. Let's say this lib is for a crate we've called aggregator, and someone else wants to use our crate's functionality to implement the summary trait on a struct defined within their library's scope. This would need to bring the trait, they would need to bring the trait into their scope first. They would do so by specifying use aggregator summary, which then would enable them to implement summary for their type. The summary trait would also need to be a public trait for another crate to implement it, which it is, because we put the pub keyword before trait in listing 1012. One restriction to note with trait implementations is that we can implement Wait, was that it? Was that the next thing? Yeah. Why is it jumping to it? Oh, because there's only one link to follow. Got it. Sorry. Where was I? I think it was one restriction to note with trait implementations is that we can implement a trait on a type only if either the trait or the type is local to our crate. For example, we can implement standard library traits like display on a custom type like tweet as part of our aggregator crate functionality because the type tweet is local to our aggregator crate. We can also implement summary on vect in our aggregator crate because the trait summary is local to our aggregator crate. But we can't implement external traits on external types. For example, we can't implement the display trait on vect within our aggregator crate because display and vect are defined in the standard library and aren't local to our aggregator crate. This restriction is part of a property of programs called coherence, and more specifically the orphan rule, so named because the parent type is not present. This rule ensures that other people's code can't break your code, and vice versa. Without the rule, two crates could implement the same trait for the same type, and Rust wouldn't know which implementation to use. Default implementations. Sometimes it's useful to have default behavior for some or all of the methods in a trait instead of requiring implementations for all methods on every type. Then as we implement the trait on a particular type, we can keep or override each method's default behavior. 10.4 shows how to specify a default string for the summarize method of the summary trait instead of only defining the method signature, as we did in listing 10.12. We have pub trait summary, and the signature function summarize reference to self return a string, now in the body. String from read more. Definition of a summary trait with a default implementation of the summarize method. To use a default implementation to summarize instances of news article instead of defining a custom implementation, we specify an empty impl block with impl summary for a news article, some braces. I want a word for that. Even though we're no longer defining the summarize method on news article directly, we've provided a default implementation and specified that news article implements the summary trait. So we can still call the summarize method on an instance of news article, like this. Let article equal an instance of news article. Fields, headline, location, author, content. The headline is string from Penguins win the Stanley Cup Championship. Location, string from Pittsburgh, PA, USA. Author, string from Iceberg. Content, string from the Pittsburgh Penguins once again are the best hockey team in the NHL. Print line, new article available, article.summarize. This code prints new article available, read more. Creating a default implementation for summarize doesn't require us to change anything about the implementation of summary on tweet in listing 10.3. The reason is that the syntax for overriding a default implementation is the same syntax for implementing a trait method that doesn't have a default implementation. Default implementations can call other methods on the same trait, even if those other methods don't have a default implementation. Default implementations can call other methods on the same trait, even if those other methods don't have a default implementation. In this way, a trait can provide a lot of useful functionality and only require implementers to specify a small part of it. For example, we could define the summary trait to have a summarize author method whose implementation is required, and then define a summarize method that has a default implementation that calls the summarize author method. Pub trait summary. Function summarize author takes a reference to self and returns a string. Function summarize reference to self returns a string. Format, read more from self.summarize author. To use this version of summary, we only need to define summarize author when we implement the trait on a type. To use this version of summary, we only need to define summarize author when we implement the trait on a type. So implement summary for tweet, function summarize author reference to self, return a string, format bang, at self.username. After we define summarize author, we can call summarize on instances of the tweet struct, and the default implementation of summarize will call the definition of summarize author that we've provided. Because we've implemented summarize author, the summary trait has given us the behavior of the summarize method without requiring us to write any more code. Let tweet equal an instance of the struct tweet, username string from Horsey Books, content string from, of course, as you probably already know, people, not a reply, not a retweet. Print line, one new tweet, tweet.summarize. This code prints one new tweet, read more from @horseebooks. Note that it isn't possible to call the default implementation from an overriding implementation of the same method. Traits as parameters. Now that you know how to define and implement traits, we can explore how to use traits to define functions that accept many different types. For example, in 10.13 we implemented the summary trait on the news article and tweet types. We can define a notify function that calls the summarize method on its item parameter, which is of the same type that implements the summary trait. To do this, we can use the implement trait syntax like this. Pub function notify takes item of type impl summary, body println breaking news item.summarize. Instead of a concrete type for the item parameter, we specify the impl keyword and the trait name. This parameter accepts any type that implements the specified trait. In the body of notify, we can call any methods on item that come from the summary trait, such as summarize. We can call notify and pass in any instance of news article or tweet. Code that calls the function with any other type, such as a string or an i32, won't compile because those types don't implement summary. Trait-bound syntax. The implement trait syntax works for straightforward cases, but it's actually syntax sugar for a longer form, which is called a trait bound, and that looks like this. Pub function notify, angle brackets, generic T of type summary, in parentheses, parameter item of type T, print line, breaking news, item.summarize. This longer form is equivalent to the example in the previous section, but it's more verbose. We place trait bounds with the declaration of the generic type parameter after a colon and inside angle brackets. The implement trait syntax is convenient and makes for more concise code in simple cases. The trait-bound syntax can express more complexity in other cases. For example, we can have two parameters that implement summary. Using the impl trait syntax, it looks like this. Pub fun notify parameter item 1 of type impl summary, parameter item 2 of type impl summary. If we wanted this function to allow item 1 and item 2 to have different types, using impl trait would be appropriate as long as both types implement summary. If we want to force both parameters to have the same type, that's only possible to express using a trait bound, like this. Pub fun notify trait bound, generic type, generic type of type summary. Oh, okay, I got this. Public function notify, type generic over summary, and the parameters are item 1, item 2, both of t. The generic type specified as the type of the item 1 and item 2 parameters constrains the function such that the concrete type of the value passed as an argument for item 1 and item 2 must be the same, because we used t in all the places. Specifying multiple trait bounds with the plus syntax. We can also specify more than one trait bound. Say we wanted notify to use display formatting on item as well as the summarize method. We specify in the notify definition that item must implement both display and summary. We can do this using the plus syntax. Pub fun notify item of type implement summary plus display. The plus syntax is also valid with trait bounds on generic types. Pub fun notify trait bound generic over types summary plus display over type summary. Okay. Yeah. Over type summary. Okay, I got this. Pub fun notify trait bound over type has summary plus has display. Item t. With the two trait bounds specified, the body of notify can call summarize and use curly brackets to format item. Clearer trait bounds with where clauses. Using too many trait bounds has its downsides. Each generic has its own trait bounds, so functions with multiple generic type parameters can contain lots of trait bound information between the function's name and its parameter list, making the function signature hard to read. For this reason, Rust has alternate syntax for specifying trait bounds inside a where clause after the function signature. So, instead of writing this, function, some function, trait bound trait bound generic over okay. So t display.clone, u clone.debug, and then t is t and u is u. Give us an I32. But I want to know how to say that in words. Okay, so we'll say in the trait bound, there's two trait bounds. Okay, so we'll say trait bound t is generic over type has display and has clone. Trait bound to u is generic over type has clone and has debug. So instead, we can use a where clause like this. Function, some function, trait bound t and u t of parameter t of type parameter little t over type big T, parameter little u over type big U, return an I32, where did they open the body anywhere? No, this is all before it opens the body. Okay, so return an I32 where T display plus clone, U clone plus debug. This function signature is less cluttered. The function name, parameter list, and return type are close together, similar to a function without lots of trait bounds. Returning types that implement traits. We can also use the impl_trait syntax in the return position to return a value of some type that implements a trait, as shown here. Function returns summarizable, and it returns a type that implements summary, and here's the body, tweet, and then that's the instance of a tweet that we created before, I guess, the same one. By using impl summary for the return type, we specify that the returns summarizable function returns some type that implements the summary trait without naming the concrete type. In this case, return summarizable returns a tweet, but the code calling this function doesn't need to know that. No, doesn't know that. The ability to return a type that is only specified by the trait it implements is especially useful in the context of closures and iterators, Chapter 13. Closures and iterators create types that only the compiler knows, or types that are very long to specify. The implement trait syntax lets you concisely specify that a function returns some type that implements the iterator trait without needing to write out a very long type. But you can only use implement trait if you are returning a single type. For example, this code that returns either a news article or a tweet with the return type specified as impl summary would not work. Function returns summarizable takes switch, which is of type bool, and returns impl summary. If switch, news article, headline, and all that, else tweet, username, and all that. Returning either a news article or a tweet isn't allowed due to the restrictions around how this impl trait syntax is implemented in the compiler. We will cover how to write a function with this behavior using in the using trait objects that allow for values of different types section of Chapter 13. Fixing the largest function with trait bounds. Now that you know how to specify the behavior you want to use using the generic type parameters bounds, let's return to listing 10.5 to fix the definition of the largest function that uses a generic type parameter. Bang. Last time we tried to run that code, we received this error. So an implementation of std_comp partial ord might be missing for T. In the body of largest, we wanted to compare two values of type T using the greater than operator. Because that operator is defined as a default method on the standard library trait partial ord, we need to specify partial ord in the trait bounds for T so the largest function can work on slices of any type that we can compare. we don't need to bring partial ORed into scope because it's in the prelude. Change the signature of largest to look like this. Function largest, trait bound, T is generic over partial ORed, parameter list of type reference to a slice of T, return T. This time, when we compile the code, we get a different set of errors. So let's see. We have help cannot move out of here. Help, consider using a reference instead. Okay. Cannot move out of borrowed content. Hint, to prevent move, use ref item or ref mute item. Cannot move out of borrowed content. The key line in this error is cannot move out of type T, a non-copy slice. Oh, I didn't read that one. With our non-generic versions of the largest function, we were only trying to find the largest I32 or char. As discussed in the stack-only data copy section in Chapter 4, types like I32 and char that have a known size can be stored on the stack, so they implement the copy trait. But when we made the largest function generic, it became possible for the list parameter to have types in it that don't implement the copy trait. Consequently, we would not be able to move the value out of list index 0 and into the largest variable, resulting in this error. To call this code with only those types that implement the copy trait, we can add copy to the trait bounds of T. 1015 shows the complete code of a generic largest function that will compile as long as the types of the values in the slice that we pass into the function implement the partial ORed and copy traits, like I32 and char do. Okay, so now we have this function largest type bound. T is generic over has partial ORed and has copy. All right. A working definition of the largest function that works on any generic type that implements the partial ORed and copy traits. If we don't want to restrict the largest function to the types that implement the copy trait, we could specify that T has the trait bound clone instead of copy. Then we could clone each value in the slice when we want the largest function to have ownership. When we want the largest function to have ownership. Using the clone function means we're potentially making more heap allocations in the case of types that own heap data, like string. And heap allocations can be slow if we're working with large amounts of data. Another way we could implement largest is for the function to return a reference to a T value in the slice. If we change the return type to reference to T instead of T, thereby changing the body of the function to return a reference, we don't need clone or copy. And we could avoid heap allocations. Go do it! Using trait bounds to conditionally implement methods. By using a trait bound with an implementation block that uses generic type parameters, we can implement methods conditionally for types that implement the specified traits. For example, the type pair T in listing 1016 always implements the new function, but Pair T only implements the compare display method of its inner type T. It only implements the compare display method if its inner type T implements the partial ORed trait that enables comparison and the display trait that enables printing. So we have use standard format display struct pair T, X and Y, both of type T, implement T, pair T. I'm just going to jump down. Conditionally implement methods on a generic type depending on trait bounds. We can also conditionally implement a trait for any type that implements another trait. Implementations of a trait on any type that satisfies the trait bounds are called blanket implementations and are extensively used in the Rust standard library. For example, the standard library implements the toString trait on any type that implements the display trait. The impl block in the standard library looks similar to this code. So, impl T display toString 4T. Because the standard library has this blanket implementation, we can call the toString method defined by the toString trait on any type that implements the display trait. For example, we can turn integers into their corresponding string values like this because integers implement display. So let s equal 3 to string. Blanket implementations appear in the documentation for the trait in the implementers section. Traits and trait bounds let us write code that uses generic type parameters to reduce duplication, but also specify to the compiler that we want the generic type to have a particular behavior. The compiler can then use the trait bound information to check that all the concrete types used with our code provide the correct behavior. In dynamically typed languages, we would get an error at runtime if we called a method on a type that the type didn't implement. But Rust moves these errors to compile time, so we're forced to fix the problems before our code is even able to run. Additionally, did I just add the word additionally? No. Additionally, we don't have to write code that checks for behavior at runtime because we've already checked at compile time. Doing that improves performance without having to give up the flexibility of generics. Another kind of generic that we have already been using is called lifetimes. Rather than ensuring that a type has the behavior we want, lifetimes ensure that a reference is valid as long as we need it to be. Let's look at how lifetimes do that.